of this acid. And by the way, how strong is this guy as a base? The weakest, isn't it? Of all the conjugate bases that are shown on that table, isn't it the weakest? Explain to me why. It's the conjugate base of the strongest acid. Why is this acid really strong? Because it gives up its hydrogen ion very, very readily. That means that this ion, the perchlorate ion, doesn't hang on to hydrogen ions very tightly. The definition of a base is something that grabs a hold of hydrogen ions, that accepts hydrogen ions. If this is not a very good hanger-oner of hydrogen ions, that makes it a pretty weak base, doesn't it? Okay? All right. Now, on the STAR exam, perhaps even the SAT-2 exam in chemistry, the subject exam in chemistry, might talk about dissolving this in water and making these. I just want to warn you about it ahead of time. That's not how we're going to talk about it. It's not correct to talk about an acid dissolved in water producing aqueous hydrogen ions, because as we said last time, aqueous hydrogen ions don't exist. In water, those hydrogen ions are attached to water molecules to make hydronium ions, aren't they? Right? However, like I said, it's typical in high school chemistry classes to talk about hydrogen ions existing in water. Right? So just be aware of that when you take the STAR exam. If you take the subject exam in chemistry, how many of you are planning to do that? Okay? When you take the subject exam, just be aware, you might see dissolving acids in water represented by this equation. Okay? Now, in this class, we talk about acid-base reactions using Bronsted-Lowry acid-base theory, that when we add an acid to water, it doesn't produce hydrogen ions, it transfers hydrogen ions to water. Right? The acid molecule dissolves in the water as a neutral molecule. It reacts with the water molecules and exchanges hydrogen ions to make hydronium ions and the conjugate base of that acid, whatever it is. So this is what takes place when we add an acid to water. Okay? Now, if you wanted to talk about another acid, down the table, pick one. Nitrous acid. Then this is what I do. Watch carefully. I replace this with nitrous acid. And I replace this with the nitride ion. So in other words, we have a whole family of chemical equations here, don't we? We can talk about any acid by just substituting the acid here and its conjugate base there. Otherwise, the reaction is the same. We okay?
Just out of curiosity, like perchloric acid and hydrochloric acid, how much stronger is one than the other?
I don't know.
You know.
I don't know.
Yeah.
Not very. There's not a lot of difference, as far as I know. They are so strong that virtually every molecule of that acid we add produces a hydronium ion. Now that's not true of weaker acids. Okay? First of all, watch carefully. What's that mean? The reaction goes in both directions, and we know that that's true. This is a base, isn't it? And this is an acid, isn't it? Find this acid on your table.
Boom.
See it?
Yeah.
How strong is it?
Very.
Pretty strong. As an acid.
Would its conjugate base be water then? Because
Yes. So here's the thing, folks. Look in. Look in. When we react an acid, any acid, with a base, any base, we make an acid and a base, don't we? Right? And we sort of highlighted that with the little pen exchange last time, right? I had the pen, gave the pen away. I went from being an acid to a base. The base that took the hydrogen ion went from being a base to an acid, right? Does that make sense then? So because we have an acid and a base reacting to make an acid and a base, the reaction can go either direction. It goes in both directions, in fact. But it doesn't go in both directions to the same extent. Which is the stronger base, water or nitrite ion? Find them on your table. You're going to look in the third column, and which side of the arrow are you going to be looking on if you want to talk about their strength as a base? The right-hand side. In the third column, the broadest of the four columns there, the acid is shown on the left, and a hydrogen ion and the conjugate base are shown on the right. So if you're talking about how strong something is as a base, you need to look on the right, not on the left. Can you find water acting as an acid? Where is it? Down near the bottom. Water is a very weak acid, isn't it? It doesn't give its hydrogen ion away very easily. You don't want to be confused by the fact that water appears twice on the table. Once near the bottom, acting as a acid, giving away a hydrogen ion to become hydroxide ion, and one near the top, acting as a base, taking on a hydrogen ion to become hydronium ion, right? Yeah. And it's shown in two different places because it's amphoteric. Yes? Water is amphoteric. Can you find something else on the table that is amphoteric? OH minus is amphoteric, isn't it? Because OH minus we know is one of our most commonly known bases, hydroxide ion, but it can lose a hydrogen ion to become oxide ion. An even stronger base.